Miss, do you think I look like Adam Sandler? People can say I look like Adam Sandler.
Stop playing. All right. Today is September 3rd, 2019. And today we're talking about functions. So specifically, to determine whether a relation is a function. I did ask you to look at example 1 and 2 on page 40 and 41. So I hope that you saw that. But if you didn't, I'm still going to talk about it. So I don't think you'll be able to finish today's assignment. A few people did in first period, but I do need you to get to the end here to practice with domain, so you'll be able to take this one home tonight and finish it. You also got to take home Friday's assignment. I hope you worked on that this weekend, and also there was extra credit, so you could have done some extra credit as well. Turn that in today as well. Okay. All right. So here we go. We're going to talk about functions. And how do you know if a relation is a function? Vertical line test is our favorite. Yes. Do you know what's so funny? I am not a big, raise your hand and answer kind of person. But my kids, my kids are young. So like my 5-year-old and 7-year-old. So when we're at the dinner table, when they want to talk, they raise their hand. I just think it's so funny. Okay, so here we go. It's not like I asked them to do that, but it's like they'll interrupt and I'll be like, Addie was talking, we need to wait till she's done. And so then they raise their hand to know that it's very cute. Okay, here we go. So vertical line test is our favorite way to determine whether something is a function or not. And so when in doubt, graph it out is a great way to go. And the vertical line test works really good if we have a graph to look at. The definition of a function, we have a function if each input has exactly one output. And that's my definition of a function. Most definitions, mathematical definitions, I don't like very much because they're too wordy, or they have lots of ifs, if and only if, or they say everything in the negative. Hate that. I don't not love you. What the hell does that mean? It's like, what, right? So I hate when there's lots of definitions like that. So this is a pretty good definition of what makes a function. An input must have exactly one output. Can it have two outputs? No, it can only have one output. And so if you want a definition, that's the definition. So let's do a little bit of practice here. Example 1, determine if the relationship represents y as a function of x. Determine if the relationship represents y as a function of x. It is. All right. Here we go. So my favorite thing to do here is we have a collection of ordered pairs. As it is, this is called a relation. Anytime we're relating an input with an output, it is a relation. And I think, when in doubt, graph it out is the best strategy for just making sure you're right. So if I were to just make a real fast sketch here, -2, -8 is like down here. -1, -1, I'm going to say is like there. 0, 0 is at the origin. I'm going to say 1, 1 is like there. And I'm going to say 2, 8 is way up here. Is it a function?
Yes.
Yeah.
Yes. And why is it a function? Each input only has one output. Also, passes the vertical line test. Okay? So yes, it's a function. Okay. Down here, letter B. Again, we have a relation. We're relating an input with an output. Is this a function?
No.
Why not?
There's threes. That sounded really stupid.
There's 3. Is 3 the problem?
No. I'm sorry.
Each input can have only one output.
Oh, it's -1.
Yeah, -1 outputs a 3 and it outputs a 4. That's not allowed. That input has 2 outputs. Okay? Also, if you weren't sure, when in doubt, graph it out. So -2, 3 is like there. -1, 3 is like there. -1, 4 is right here, stacked on top. 0, 4, and 1, 5 is like there. So again, if you were to draw a vertical line, right here, we hit 2 points, and that is going to fail the vertical line test. So it is not a function of x. It's not a function of x. Okay, that says fail. I know. All right. So when in doubt, graph it out. It's my favorite saying. We're going to do a lot of graphing today. Here we go. Letter C. How do we know if this is a function of x? Graph it. When in doubt, graph it out. That's a great strategy. Does anyone know what the shape of this is? It is a circle. Very good. Remember we talked about circles. X being squared, x squared plus y squared equals r squared. Radius squared. This is a circle. Now, maybe you knew that already. If it's a circle, is it going to pass the vertical line test?
No.
No, it's not. But how do we know for sure, in case you didn't know? So how do I graph this? Got to isolate the y. So I have y squared equals, I'm just going to say 16 minus x squared. And then what do we need to do? Square root. What do you have to remember when you take a square root? You need the plus or minus, and that's really important. So when we graph this, there are 2 equations. The positive root 16 minus x squared and the negative root 16 minus x squared. And you'd have to put those in y1 and y2. What would happen if you forgot the plus or minus? It would be a function, which is a problem. It's not right. So it's really important that you remember the plus or minus here. The square root of 16 minus x squared and negative square root of 16 minus x squared. When you graph these, zoom standard, you're going to get a lovely egg shape. How come it's shaped more like an egg than a circle? It's not square. It's not square. My lengths here are slightly larger than, or my width tick marks are slightly larger than my vertical tick marks. So I can do zoom square, and you'll see slightly better shape. All right. Does this pass the vertical line test? No. You can see it intersects 2 times. This fails the vertical line test. It is not a function. Not a function of x. I also want to point out that your calculator, the newer calculators do a better job because they have smaller pixels. Okay? These old calculators and their giant pixel size it doesn't graph because what happens is the calculator says to it, so you can see how it looks like there's a little gap, right? You see how it looks like there's a gap? It's really not, okay? Your calculator says, I know I'm not allowed to graph a vertical line. And once it has to graph too much of a pixel, it just, its default is I'm not going to graph that pixel, okay? But know that it does actually go all the way around. All right. Questions on those? All right. Find the domain of the function. Verify graphically. Find the domain of the function. Verify graphically. Okay, today on these I'm going to be doing a couple things. I'm going to introduce two ways to show domain to you, two ways to write domain. So I want you to start thinking about both of them. You have to know how to use them interchangeably. So first of all, we've talked a little bit about domain. Today we're working a little more with it. But I like verifying graphically. A lot of this class is figuring out how to use your calculator to justify, to verify what you're doing. And so graphically, domain means for what values of x, for what values of x is there a graph? Meaning, where do you see the picture? For what values of x on your calculator do you see a picture? Okay, and so we can do a couple of things. I mean, if we want, we can look at the graph first to get an idea. All right, so I'm going to just start there. I want to plug letter A into my calculator. What do I need to do if I'm going to graph this rational fractional function? Can I just type it in 1 divided by x squared minus 9?
Parentheses.
Parentheses around what?
X squared minus 9.
Yeah, the whole denominator. You absolutely need those parentheses. X squared minus 9. So I've put that denominator in parentheses. And then I'm just going to do a zoom standard, and you can see, oh, it's kind of weird looking. Huh. Not a great picture. So I'm going to change my window, and I'm going to do a zoom decimal. Zoom decimal brings it into like a 4x4 window, -4 to +4. And you can see a little bit more of the graph. Now, again, it looks like it just stops. But does it really just stop there? No, my graphing calculator, again, is just running into a problem that it's like, I can't graph anymore because then I'd be graphing a vertical line, and that's not allowed. It does go on forever, okay? But you'll notice that here, our graph appears to be going up towards positive infinity. Then on the other side, it's going to negative infinity. Where our graph diverges, where they go in two different directions, what we have is an asymptote. That's a value that's not included in the graph. And there's another place over here where we diverge. One goes to negative infinity, and here we go to positive infinity. Separating the two is an asymptote, another value that we exclude. You can also see that in the table. If you go to the table, look at what happens at 3. Error. What happens at -3? Error. Error. Not included in the domain. Okay, where you have an input and an output, that's part of the domain. Okay, where it doesn't work, not part of the domain. So where does that come from? What do we know about rational fractional fractions? Denominators cannot equal 0. So I'm going to take my denominator and say x squared minus 9 is not allowed to equal 0. So what can we do? You can solve. Can you factor this? You could double bubble. Can I just move the 9?
Yeah.
Okay. And then how do I get x by itself? Square root. So, and what should I remember? Plus or minus. So here we have x cannot equal plus or minus 3. That's one way to write domain. This is inequality notation. All other x's work. So your book might say all real numbers except x equals plus or minus 3. Okay, so they're taking those out. I want to talk about interval notation. If I were to graph this on the number line, I would have -3 and +3. And since I'm not allowed to equal negative and +3, do I use an open or closed circle? Open. Okay. Those two values do not work, but everything to the left works, everything in between works, and everything to the right works. If I wanted to write the domain using interval notation, interval notation says what are the intervals that we're allowed to use. How far to the left does this arrow go? -infinity, yeah? We use a parenthesis. Why do we use a parenthesis? We can never equal it. Okay, we can never get there. Am I allowed to equal -3? No, so I gotta stop there. I gotta use a parenthesis. So from -infinity to -3 is one of our intervals that work. Then I gotta pick up on the other side of -3, and I get to go from how far?
3.
To +3. So we say union -3 to +3. Again, why am I using parentheses? Because I'm not allowed to equal it. So brackets have the built-in equal sign. And we say there's a second interval, so we're going to union, U for union, the third interval. We pick up on the other side of 3 and we go all the way to +infinity. So there's our third interval from 3 to +infinity. So this is the same thing using interval notation. Okay. Okay. So another great thing about using your graphing calculator, I'm going to look at letter B here. I'm going to go back and graph this guy. This is a cube root function. So if you're on a TI, then your cube root is under the math menu. So you would go to math, and then the cube root is number 4. So there's the cube root of 2x minus 5. I think on the Casio, yeah, on the Casio, they have a second function. Oh, is it +5? Thank you. Thank you. So the Casio is actually easier and faster to get to for the cube root. So when I look at this graph, oh, hey, that's interesting. This is a breaking wave graph. I have dreams of surfing. Well, that's what I call that, the breaking wave. Do you see it? Do you see the breaking wave? Like that's where you're paddling, and it's starting. Okay. All right. So.
I thought we got sucked into a wave. The lifeguard told me to get out, but I couldn't swim.
Yeah, I had to be rescued once. Okay.
Nobody thinks
Okay.
It was like a hike.
So domain. As I said, when you look at the graph, when we talk about domain, we ask the question, for what values of x is there a graph? Well, when we look at this breaking wave graph, how far to the left does it go? It goes to -infinity. And then how far to the right does this graph go? +infinity. If we want to know what values of x, all we have to do is look at the x-axis. and ask ourselves, well, how far to the left does that graph go? It's going to go on forever. The domain of this function is negative infinity to positive infinity. It goes forever to the left and forever to the right. So if you have a graph, you don't have to know anything about domain. If you can imagine, that graph goes on forever. This is an odd root. Odd roots are really easy, okay? So the last one, a little harder. So you might have this, and you also might have x is just all real numbers. This is a way to say that, all real numbers. I don't know how your book does it. Okay, you can use the boldface R or say all real numbers. Every value of x works just fine. Okay, over here, we have to combine a few things. What do you know about this function f of x here? It's got a couple of things we have to consider. Okay, we got a denominator. What do we know about denominators? Denominators cannot equal 0. So x plus 2 cannot equal 0. We will graph it, so, you know, I heard you. We'll do it in a little bit. You weren't wrong. And so how do I solve for x? Okay. So that means that x cannot be -2. So this is one part of the domain. I'm going to graph that on one number line. Here I am at -2. Do I use an open or closed circle at -2? Open. Okay. X equals -2 is excluded. We're not allowed to be -2. Does everything else work for this? For that, yeah. For that part of our function, everything else works. But we have another part. What about this even root? What do we know about even roots? That's only when you solve. This was given to us. Can I take the square root of -9? No, what is it? It's imaginary, right? Can I take the square root of negative numbers?
No.
No, they're imaginary. So what must these values be? Greater than or equal to 0. Even roots must be greater than or equal to 0. That is the second part of the domain that we have to consider. I'm going to square both sides. So I have 4 minus x is greater than or equal to 0. Can I move the x over? Sure. So this says x must be smaller than or equal to 4. So I'm going to draw a second number line. Here's 4. Open or closed dot at 4? Closed. Solid dot because it's equal to. And what way do I want to shade? To the left. Numbers littler than 4. Littler would be to the left. Okay. Now, when we have multiple components to domain, we have more than one thing that we have to consider. The solution is where they overlap. Okay? What works for both? Where is the overlap? Okay, that's the question. So I'm going to start way over here on the left-hand side. Do they both go to negative infinity? Yes. So they both go to negative infinity. And then we come along, we're moving along to the right, and where's the first little hiccup? At -2. For the pink portion, are we allowed to have -2? No. For the green, are we allowed to use -2? Yes. Does that work for both? No, it does not. So we cannot include that. So for our domain, we're going, the first interval is from negative infinity to -2. So now we're going to pick back up on the other side of -2. And then where's our next little hiccup? 4. So on the green one, does 4 work? Yes. On the pink side, does 4 work? Yes. So does it work for both? Yes. Bracket or parenthesis? Bracket, because we're allowed to equal 4. So our second interval starts at -2 and it goes to 4 with a bracket. Do we have a third interval? No, because it works for pink, but it doesn't work for green, so we can't include that. So this is the domain in interval notation. So I want to show you what that looks like graphically so you can see how the graph shows this domain. We're going to see a picture from -∞ to -2 and -2 to 4. So on my numerator, I have 4 minus x divided by the x plus 2 in parentheses. So remember, if you're putting this in your calculator, you need parentheses around that to denote the denominator. Okay, I'm going to do Zoom standards. You can see. All right, so it looks like it goes forever to the left. That'd be -∞, and we're coming along, and then right here at -2, the graph diverges. We have an asymptote there. That's why -2 isn't included. Okay, and then it picks back up on -2, and we see, and it seems to stop at 4. I'm going to also look at the table and show you the table. You can see at -2, what do we have? Error. -2 is not part of the domain. It's not included. And then when we continue on, you see that we have an output for 0, but after 4, I have error, 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 error. Nothing to the right of 4 works. Okay? So all these things can be verified with your calculator. Okay? Do you have questions for me? All right. We can get started.